So, okay, so this is my first attempt to do something in systemic risk. So actually I have a couple of young people with whom I started various projects. So this is one which started actually with a master student, Lukas Reichel, and Oliver Klei, who's a postdoc, and he will be here also starting next week. So, okay, we have learned already about core-periphery banking networks, so that's great. So, and the outline of my talk is that I will recall this model, and then I will say something about, you can call it a risk measure if you want, not in the strict sense as people have started to do that 10 years ago or so, but it's just a financial robustness measure, and then I will say something to risk management applications, which were mainly done by this master student. Okay, so our market model is a weighted directed graph. So it has nodes, which are sets of agents. They are banks, financial institutions, and we have capital N of those. And then, well, the EI are actually credit portfolios. So meaning that IJ, so an HIJ, belongs to EI if agent J is a creditor of agent I. And then, well, we have a weighted graph, so the WIJ as a proportion of agent I's total credit amount issued to agent J. And then, well, we have the number of institutions which actually get money from institution I, and this is a V out, and this means we have an out decree which is given by the number of credits issued by agent I. So this is the formal setup. And when you look at this, well, I talk about something like this, which I stole from Rama actually. So that's the Austrian network, and of course there are many around now, and they all look a bit like that, and this means that they all have a core-periphery structure. So that means we have an adjacency matrix which is blocked. So we have here, this has been mentioned before more or less. So we have actually 4 blocks. So we have core banks, so the C stands for core. So it means the CC block gives the credit relations among the core banks. And then we have a PP block, which will be 0 in the end, gives the credit relations among periphery banks. And then we have PC, which stands for the credit from periphery to core, and CP the other way around. Yeah? So this would be now our block adjacency matrix, and I will specify this during my talk, so more and more, and so that we can actually do something with it. Okay, so and early on in this work, I was talking to Ben Craig from the German Central Bank, and they actually have a paper where they exactly will do this. So they somehow motivated our model. So, and they specified these blocks as follows. So CC is a matrix of ones, exception to the 0 diagonal. So it means all core banks will issue credits to all other core banks. And then the periphery banks, well, they do nothing with each other. And CP, well, is row regular. That means each core bank issues credits to at least one periphery bank. And PC is column regular. This means at least one periphery bank issues a credit to one of the core banks. So that was actually their structure they suggested in this paper, and they also did some empirical analysis, and which actually then gave them obviously the idea to formulate the specification like this. Okay, well, and then this master student I mentioned, well, he actually wanted to read Battiston et al.'s paper, and well, somehow I was a bit surprised that, well, what they actually do, well, we are among us and he's not yet here. So let's say I didn't understand much and also didn't understand why, and the math was not very clear. So I was a bit annoyed and started thinking myself, okay, don't give me away. Okay. Anyway, so, well, people have been doing similar things, of course. Yeah. So in particular, Fug and Sun, well, they looked at what people call a homogeneous model. So what we do here is we model the system's financial robustness by a vector Ornstein-Uhlenbeck process. Well, this is a very simple model. One can deal easily with it. So that means we have a dynamic, well, we have actually the theta, they are just a diagonal matrix. So in each row, we would just have some parameter. And well, say somehow, I will make this more precise, they are parameters of the agent's interbank activity. And then we have our weighted adjacency matrix, which I have presented before, and well, we have these weights which actually add up to 1. And yeah, so this is kind of an Ornstein-Uhlenbeck structure, and what we see in this drift term is actually the interdependence from agents' interbank market activity. So when we look at this equation, you will understand this better. And well, usually people take Brownian motions, but well, we can easily work with the Levy process, makes no difference really. So that means
I guess the matrix you've got in front of the row there is effectively it's a Q matrix. It's a Markov chain intensity matrix, if you wish, because it's got rows of 0. Okay.
So of course it has a Markov structure, that's clear.
So if there is no network, then each bank.
Oh, the network is in the A.
And that's it.
So the network is in the A, and
but
so
A is 0.
Sorry.
So I don't think. What's the role of?
Let's look at
the assumption
this.
that the row sums of the A are equal to 1, isn't it? So okay. You can't have AW equals 0. That's not allowed.
That's not.
Yeah. So it, after all, well, no bank lends money to itself.
I mean, if there was no activity at all the equation would say is d rho equals dl.
Yeah, that's true. Okay, so that means when we look at a single agent's robustness, well, we have an equation like this. Yeah? So, well, we have this agent's interbank activity parameter, and then, well, we have this Ornstein-Uhlenbeck structure, but actually here, well, we have a random object, and this random object here gives you the interaction between I and all the others. So that's what you see here. So that's a weighted mean of all the creditors. So that means the financial robustness of bank I is influenced by all its creditors. So that's the idea. And well, as I said, well, actually in these two papers, you find this model in a homogeneous way. So meaning was the Wij, so you have no core and periphery, you have all banks are just the same, and the Wij are just 1 over n, so we have n banks. And obviously this comes from statistical physics. So people have been looking at mean field models in statistical physics. And of course, when you think of physics, each particle behaves like the other. So a homogeneous model is a natural model in statistical physics. But to translate it into finance, I think, well, it needs a bit more structure. And so what we did here is we just changed this, well, people call this the McKean and Vlasov model, the homogeneous model. So we just changed this to a model with a block matrix. So that's what we did.
Can I ask,
yeah.
The Battiston reference, is that to the debt rank measure?
No, it's a paper with Stiglitz and Green.
Okay.
Okay, so this is now our model. So it reflects this core-periphery structure in a certain sense. Yeah? So of course we have to specify this by specifying the weights. So okay. Now, well, what we do here, well, we think of this market. We have core banks, and we have periphery banks. And now the question is, well, what influences financial robustness of a core bank? Well, it's influenced by all banks which are creditors of the core bank, which are actually, in my model, all the other core banks, and all the periphery banks. And then, well, actually here for the driving process, I allow a levy process. They are all independent, these levy processes, and I allow for a specific sigma, which is the same for all core banks. Okay, now, well, this means, well, the financial robustness of the core banks is influenced by, well, all the other banks. So now, well, what happens to a periphery bank? So a periphery bank is influenced, they don't interact with each other. So periphery banks only interact with core banks. So it means, well, they are actually influenced by, well, all the core banks. So, and here we allow for a different parameter sigma, well, in front of our levy process, which we assume to be standardized. So that means we have here independence in these, well, what we think of, let's say, well, market. Yeah, okay, so there's a market risk, which is given more or less here by this, and the market risk may have a different, may have different influences in core and periphery. We could think of that. Okay, so they have different parameters. And then the Li are all identically distributed for all I and C. And for all K and P, they are also identically distributed, but they may be different. Okay, so that is more or less our model, and now, well, so that means we have we model now how the interaction works, and now we have to specify the W's. Okay, and this is how we specify the W's. So in a way, what we do, we assume homogeneity in these different blocks, because in the end I want to derive a mean field limit, and I need some regularity for that. Okay, so we have our core banks, and well, here the Wij are just given by 1 minus epsilon, and then, well, just the number of all the core banks with which a core bank interacts. And then for the periphery banks, we have just weights epsilon divided by the number of periphery banks, and, well, these they add up to 1, and that's it. And for the periphery banks, we actually have weights which are all, so that's a homogeneous model with respect to the core banks. Yeah? So there's homogeneity in that, but for all K and P and for the core banks, we have actually this, well, double homogeneity structure, you would say. Okay, and well, our main theoretical result is actually a mean field theorem, and it gives you the following. So in the end, what you do is, it's a law of large numbers you prove here in a systemic way. So it's the mean field limit here is given like that, so they are always indicated by a bar. And now, well, you have here, instead of means, you have here expectations all over the place, and, well, then you have, well, same noise. And what you actually prove is you prove that the two systems, so the system described by these equations and the system described by these equations, that they actually, the systems converge to each other given the number of particles, banks in my case, so goes to infinity. And I have to specify this, what it means, because, well, the number of my banks is capital N, and I have them separated into core and periphery. And then, well, actually, the mu c, so these are expectations, they are given by that, and the mu ct is a distribution of this guy, and the mu tp is that of this guy.
Have we got any assumptions on the L, the Levy process?
Yes.
It should be reasonably decent, otherwise you wouldn't get a strong law, I guess.
Yeah, that's true. So here, all assumptions should be here, I hope. So we have this core-periphery model. So I is always the index for core, K is always the index for periphery. And then we have, well, these friction parameters, theta C and theta P. We have independent standardized driving Levy processes. So this possibly different sigmas. They are identically distributed for all core banks and identically distributed for all periphery banks. And then, well, we have defined this mean field system. So, and then what you do is you take the same friction parameters, the same Levy processes, the same sigmas in both systems. You start with the same initial conditions, independent of all Levy processes. And then, well, you define a distance or a uniform distance on a compact interval between two processes. And then, well, this is now the result. So what we have is that, well, this guy here remains bounded. So for all banks, not only core, but also periphery. So for all banks, we get actually this result. And what we need is, and this is debatable definitely, so we need that the number of core banks goes to infinity. Fortunately, it goes the right way around. So I could think of that number of core banks increasing, let's say, logarithmic, and the number of periphery banks, which we assume is much bigger, could be algebraic or exponential or whatever. So that means, well, at least, well, this result covers that we can have many more periphery banks than core banks. So this is our result, and what I wrote down is the new propagation of chaos result, because what you should notice is that actually all these equations are independent. So because the Levy processes are independent, and here, well, the interaction here has been replaced just by means.
Don't you need some sort of moment conditions on
Second
those?
moments, didn't I write this down? Okay,
Yeah, right.
somewhere in here.
Oh,
Here.
right.
Yeah, so
Yeah.
I standardized my processes,
Yeah,
but I
right,
need
okay.
second moments,
okay,
that's
fine.
clear. Yeah, okay.
Sure.
Yeah. Okay, so that's the main result. And well, it's the first mean field result I ever proved in my life. So,
So sorry, could you,
Sorry?
Could you explain it a bit more? The result, I'm not sure I fully see. Could you explain it in words? What is the result?
well, the result is actually that, well, when n goes to infinity, or let's say, I should say, when the number of core banks goes to infinity, meaning by this condition also the number of periphery banks goes to infinity, then, well, every single bank, every single robustness of a bank I goes to the robustness of the mean field model, in this sense, with a certain rate. Is that good enough? Okay.
So we was saying in the mean field limit, all the periphery banks behave like this row bar process. So you have a single equation for core banks, a single equation for the periphery banks.
Yeah.
Okay. Good.
So in effect, they decouple completely.
They decouple completely.
Each
Yes.
one is an independent copy of the other.
It's the previous slide.
Here, yeah. Yeah, so they are all independent. Yeah, so all these guys, all these financial robustness, we call it, they are all independent.
But that's because in the initial model, there is no common noise.
Yes,
So you expect that.
yeah, it's true. Yeah. And as I said, it's the first result, and Carsten started working on more general things already.
So here there is nothing really special about the core-periphery structure. It's just about having two groups, no? Or is it?
Yes.
It is something that depends.
Yes, it's having two groups. Yes.
So the graph doesn't play a
it's complete.
Well, it depends how you mean that. Well, here actually what you have here is more or less, well, these, you have these, where I say, hey, here. So it means, well, we specify these guys. Yeah, so that is a graph, isn't it?
If you go forward to the result,
Yeah.
to the result, the weights disappear, really.
The weights
If you show
disappear.
the result, the weight, yeah.
The W matrix.
The final, the theorem, your
No, well, I specify them,
but if you
so
go-
in a certain homogeneous way, they don't
But
disappear.
that's not the, here.
Here,
Yeah.
should be complete.
So here actually these are the W's
They're supposed to
in,
be equal in effect, aren't they?
yeah, they are equal. It's not a homogeneous model on the whole banking network, but it's homogeneity within groups.
Okay, so.
Yeah? So,
That's what he's saying, two
Yeah.
groups.
yeah, it's two groups, yeah.
Just one quick question. In fact, if we were to have multiple groups, it would be the same, right?
Yeah, as long as you have
Yeah.
finitely many.
Yeah.
Yeah.
Finitely many, it could be.
Yeah.
But here you could have, so this is, you choose to do it this way, but suppose you have a finite core, like 10 big banks, and then you have thousands of small banks.
Yeah.
So you could do the mean field limit on the second, on
Yes,
the periphery.
yes, Carsten
But-
is doing this.
Keep it finite in the core, and then you will have the
Yeah.
Wij there
Yeah.
without them
I
disappearing.
guess so, yeah. Yeah. Okay, so and well, as I said, my first mean field limit result in life. So, and well, the way how it's proved is actually, well, I studied an old paper by Ara Schnittmann. He actually did the homogeneous model. So it's an old lecture note, a Sanfluor lecture note. And it's written up in a very nice way, so everybody can understand it. And what I did is actually, I went through his proof, and I just adapted my model to this proof. So you need to fiddle a bit around with it, but it's not that complicated. And let me just explain a little bit. So what is the, or maybe I should not. Okay, so maybe I should go to my risk management applications. Yeah, so that means here, well, we just modify Ara Schnittmann's proof, and well, it comes out nicely, and you get exactly what you need. You have to fiddle around a bit with all these, with all these epsilons and the different groups, and well, but use more or less the same arguments. You use Cauchy-Schwarz and the independence, and you use Cornwall's lemma and so on. So it's just straightforward. So, and you find it in my paper. Okay, so now we have been thinking how to make use of this. Yeah, so, and I show you a number of rather simple things, but in the end, what I like is that, well, things come out as you think they should. Yeah, so it's not so that it gives you well, a lot of extra insight, but it tells you the model is so that it captures certain facts which you can believe. Okay, so here in this first left figure, you see a simulation of 5 black robustness processes of the 5 core banks. So, and also you see 5 of the, well, 50 periphery banks in red. And they all start with their financial robustness in 1, and they move on in time. And the parameters we choose are the friction parameter theta is equal to 1, and the sigma is equal to 0.2 for the, bless you, for the core and the periphery banks. Yeah? So that is the situation. So you see just 10 sample paths, well, with the same models, with the same parameters, and well, the interaction is as I described it to you, but there's no limit involved. So it's just the original model, well, with specified weights. This is what you see. Now you can think of this driving levy process giving you something about how the market behaves. So that means, well, the market volatility is at the beginning given by sigma p equal to 0.2. And in this simulation, I forgot to say, we have just Brownian motions as driving processes. Okay, so now assume that the market volatility changes. So it changes from 0.2 to 0.5. So what happens? Well, a core bank, well, they have big risk management departments, they have clever quants, so maybe they can actually hedge away this increase in market volatility and remain with the old parameters. So a periphery bank, however, well, they don't have these clever guys, and well, they don't have the means to do that. So that means if they don't do anything, well, all these red paths, they change to what you see here. Yeah, so it's the same seed which we have set here. So that means, well, of course, the core banks are a bit influenced by this because, well, they interact with the periphery banks, but they are mainly determined by their interaction with the other core banks. So it means these black sample paths, they do not change a lot, but the red ones, of course, they do. So now what can a poor periphery bank do? Well, they can, for instance, well, increase their engagement with the core banks. So they can increase, well, their investment into the interbanking market. That would mean they increase the theta. So that means, well, that they are drawn much faster to the core banks where they are drawn anyway. So, and this is then what happens. So if the periphery bank increases theta p from 1 to 6, then, well, that is what happens to their sample path, to their financial robustness. And if they increase the theta p even to 15, then, well, you see actually this pattern. Yeah, so I think that's not too unrealistic and explains a little bit the model. Okay, so now the next question is, can we make this, well, mathematically perhaps a bit more precise? And now, well, when can we calculate things? So you should notice that, well, stationarity is actually not guaranteed in this case here. So we have means which depend on t and nobody knows. So, but however, if the mean field limit is a stationary process, then we can do more calculations with this Ornstein-Uhlenbeck structure. So a lot is known. And this means, so provided the mean field system has a stationary version, then actually the agent's robustness solves, well, this classic Ornstein-Uhlenbeck model. So, and this mu is just, well, the mean of all the core banks' robustness. The bar should be away, I'm sorry. So that should be the rho ti. So that means now, well, when we are in this simple Ornstein-Uhlenbeck framework, then of course, well, lots of things are known which we can use. Okay, so for instance, we can formulate risk measures. So for instance, the standard deviation risk, you can just calculate the standard deviation. It's known for 100 years or so, I guess. So you can write it down like that. And you see it involves the variance of the volatility of the market, but also the friction parameter, which explains that you can play with these two. So, and then, well, you can also formulate an inverse first passage time risk. So in calculating, well, the expected first passage, which you can interpret as a default time, of course, and then, well, this gives you another risk measure. So, and for this, actually, it's known, well, what this expectation looks like. Yeah? So you can write it down for a standard Brownian motion, as we have been simulating with this process, all starting in 0, all processes. And then, well, you have this nice formula. Well, here you see again well, the standard deviation risk and the sigma square. And phi bar is the tail of the standard normal distribution. Phi is the normal density, standard normal density. And so you have an explicit analytic expression for this guy. Yep.
I think maybe I'm lost. So the standard deviation risk of the periphery does not depend on the sigma of the core?
No, you have to read it as two equations. So you have a TC.
No, sorry.
Where are you?
SI is for the core and SK for the periphery.
Yes, and the C is for the core, and the P is for the, and the K and P are the P.
That's totally independent.
Yeah, yeah. Mm-hmm.
What's the intuition behind that? So,
Well, it's first the mean field limit, which is already independent, and then it's the Ornstein-Uhlenbeck, which is a stationary model.
But in what sense is that the core and the periphery? Why can't you swap the indices? At this point, it's the same.
Yeah, of course.
Formulas are the same.
They have just different.
But in the initial model, it's not the same. You want the core to.
Yeah.
It's not symmetric being core and periphery in the
No,
initial graph. But
no.
here it's symmetric.
Yeah, well, that comes from the mean field result. So where is it?
Yeah, I
So-
understand. So maybe that means the scaling limit.
So
There's something.
So the point, so here I have
Not
two,
exactly.
I have two different limits here. Yeah, so I have two. Now, when I assume that we have a stationary model, then actually they become the same. Because, well, here, this here would be the mean of the periphery banks down here. Yeah. Then I have here the mean of the periphery banks already, and I plug it in here, so I get here the same means.
The complete core-periphery, yes?
Sorry?
This is a complete core-periphery network, yes?
Yes.
Every periphery is connected to all core.
The periphery banks don't
As
interact.
in the equations, when you...
So the periphery banks
one
only
divided
interact with
by
the core.
Yeah, yes.
So every periphery bank talks to every core bank.
Every core.
exactly.
Yes.
Same way.
So that's why
Yeah.
it's symmetric.
Yeah. Mm-hmm.
So it's just by parity.
But there's also symmetry between the core and periphery in that case. So.
Yeah, so if you have, as I said, well, I boil it down more and more unrealistic things, you can say. Yeah, but that's how it is. Okay. It's the first paper of that kind, so be patient what's coming. Okay, so now, well, we are here. Okay. So now, well, we have here these two risk measures, and we want to interpret this in the context of our model. Okay, so, well, what would a bank do? Well, it would probably fix a target value for its standard deviation. Yeah, so, meaning, so when the theta p, when the sigma p, well, the market volatility is changing, then, as we already understood from the simulation, the periphery bank can hedge by modifying sigma p, and here now we know how. Yeah, so, for instance, in this example I gave you, we had a sigma p of 0.2 and a theta p of 1 that corresponded to a standard deviation of 0.1414. And when we assume a change of the external market risk to sigma p point is equal to 0.5, then we know exactly how to choose theta p to have the same standard deviation risk. And this corresponds then to some more investment into the interbank market. Okay, so all this works well. However, of course, there's a problem when the mu is too low, because, well, when we think of a default risk, then it's clear when the mu is close to 0, then the bank may default when they just invest more into this interbanking market. So that increases their default risk. So it brings them close to the mean of the core banks, but if the core banks have a low mean robustness, that may be exactly the wrong strategy. So, okay, so let's look at that. So we have this, well, let's call it a default risk, so the inverse first passage time risk. Yeah. So, and here, well, you see how this now works. Yeah. So we have here different graphs. So we have, let's start with that. So on this axis, you have the theta p, which gives you a measure how much a periphery bank invests into the interbank market. So going like this means they invest more into the interbank market, meaning they get closer to the mean robustness of a core bank. So as long as mu is high, so meaning when we look at these lines here, well, that's not a bad strategy because, well, their default risk actually decreases. However, when mu is 0.1, which is a yellow line, or even 0, which is a black line, of course, this is completely counterproductive. So, and here now, that is my last slide. So what happens now here? So there are two situations here. So here actually mu is decreasing. So meaning the mean robustness of the core banks is decreasing from 0.5 to 0.1. And now, well, if now sigma changes from 0.2 to 0.5, and well, this periphery bank is do nothing, then what you see here is their default risk. So it increases linearly when mu decreases. However, if they actually increase their interbank assets, then what happens first is, well, they remain here below the value when they do nothing, but after a while, actually, they do worse when they increase their interbank assets. So when there's a point from which on they should definitely not do it, and it's when mu falls below 0.3. So, okay, so that's it. References, and well, thanks for your attention.
So in your mean field analysis, you don't go to the mean field partial differential equation level at all. So you have your ensemble of particles, and then you prove something on an arbitrary representative particle against the average evolution of the expectation.
On every particle, yeah. Mm-hmm. Okay. Yeah, well, it's probabilistic proof. Mm-hmm. Chris? Mm-hmm.
I mean, how do you sort of interpret this row? I mean, what is it? If I was going to try and apply these results, what market variable would I look at to say that's rho?
Yeah, good question. You should ask Battiston and Fouque and Sun and these people. Yeah. No, actually, Rama asked me the same thing already. So,
in the paper of Battiston, rho is like something like a credit rating. So it's like an indicator of the financial health of the bank I. So that's how we interpret it. But in Fouque and Sun, they don't say what it is. And it's not the same dynamics.
I saw a presentation by Fouque, and for him it's more like a liquidity parameter, how much liquidity the bank has. And then he has an interesting, and then there is also a parameter about more liquidity from the central bank, and it turns out that this liquidity will not matter after all.
No, but the equation, can you show the equation?
yeah, it shows the equation again, and then we can discuss it.
So
I'm looking forward to get some help with that from you. This one or this
like
one?
the first one, yeah. Yeah, but let's look at the simplest one, like the homogeneous one already to understand what.
This here?
Yeah, so so suppose rho I is an indicator of health of bank I. So how do you interpret this Untitled dynamics?
But if you turn it around, you can also think of it as a risk.
Could it be like a CDS spread or a bond spread? Maybe no.
Yeah, well, whatever, but so the equation says the indicator for bank I is mean reverting to the average of the indicators of the banking sector. So what this does is that in a period where what this does is that the spreads will all increase together. There'll be periods of low spread and periods of high spread, but you can't have a very large heterogeneity of the spreads because the interaction term draws them together.
It's similar
This is
to
what I understand.
Mm-hmm. Yeah. Mm-hmm.
It's also similar to like models in social opinion dynamics, for example. So if you have opinion aggregation, it's usually modeled.
Yes, but why does it make sense for banks? This is the point. Because social opinion dynamics, I conform to the average opinion. We understand what that is, but what here, rho I is not the decision.
Systematic.
What is it? I mean, what is it? I mean,
Yeah, so
how can we
question.
discuss the meaning of these equations if we don't understand what these are the equations for?
Exactly.
Common exposure.
Why should this variable, whatever it is for bank I, depend linearly on the variables for the other banks? I mean, if we think of these as perhaps some measure of the assets of the bank, then why should my assets depend linearly on the assets of some other bank? Don't know.
It could be how much liquidity they want to give, some kind of measure, because then you say, oh, maybe if I get more liquidity from the others, I also give more liquidity.
But so there's something about Chris said in the beginning. So the way the equations are structured, the matrix is special. It's the rows sum to zero. What's the interpretation of that? Why do we have that? If you go back a few slides, in the beginning you have the...
Yes,
Yeah,
this
yeah.
one. Mm-hmm.
So...
Well, but this comes really from thinking of like this, so that you have here, you have all the other robustness, all the other robustnesses,
so
and
if
what
you look
they
at it
are.
like this, because the weights sum to 1, this can be anything like asset size or reserves in dollars, because the weights don't sum to 1.
Mm-hmm.
So this should be some normalized variable like the spread, otherwise it doesn't make sense.
Mm-hmm.
It has the same structure as these Google eigenvector problems. So if you look into a stationary state, the stationary state is going to be an eigenvector for the eigenvalue 1 of the matrix. So it has that same structure, but I don't know if that's a...
So that's the Einstein-Uhlenbeck thing involved, yeah. Mm-hmm.
So it's like saying like in Google your rank depends on everybody who ranks to you, so it would be kind of a rating that depends on your own rating is a function of everybody else's rating of you. It's that kind of...
On this complete core-periphery structure, right? Because so what happens if peripheral bank creates links with all core banks, and that will go to infinity to get you concrete results. Now we also actually consider sort of minimal core-periphery networks where you only have one link.
Sorry, I didn't
So
understand
suppose
that.
that you have a core-periphery network where each periphery bank has only one link.
Yeah. Oh, you can play with this model essentially, but I think people are right. One should think about what stands rho for in this banking world. So how would one actually, well, what data would explain the rho?
And is it so important that W is normalized? What happened if it wasn't? One. What happened if you let it be?
Well, you can always normalize it.
So then you can absorb it in theta I.
So then
Yeah, so you can always normalize it.
You don't need it to be just normalized.
The either weights go to 0 if k goes to infinity.
One thing you'll find with this is, I mean, if you just keep the C and the P absolutely fixed, you don't, so, but consider it as T increases, you're not going to get this row process. It's not going to be stationary the way you've set it up.
No, that's clear. So because I always have this randomness in there. So
Sure, but
the random interaction remains the same over time.
Yeah, but it's not. But the thing is, it's the matrix of the linear system there has got a 0 eigenvalue, so you're not going to get something that's like an AR1 process that's got a steady state distribution. The variance is just going to increase without limit. I don't know if that's I mean, then it sort of starts to make it a good question. What can this row actually be? It's something which cannot be imagined to have a steady state distribution.
So, but what would it be then?
Well, that's not my model.
No. It's true. No, but when you say, well, that would make it a better question, so still the question remains, what is the role really?
I mean, I think you've talked about default and sort of mean time to hit 0 and stuff. So it's I think maybe that interpretation of this row as being some sort of distance to default thing might actually be.
But in this model, there's no default, right? There's no default.
Well, I introduced this first passage time risk, which is a...
Yeah, but at the first passage time, nothing happens. It continues to evolve.
Yeah, well, you can do it, of course, you can do an absorbed model.
Yeah, but then it gets more complicated.
Yeah, of course, sure.
You could say that when row hits row I hits 0, then
it stays 0, yes.
But at that point, it starts to then row to me is some sort of measure of the assets of the institution, and then why should my assets be impacted linearly by other people's assets?
No, you could think of it as a Fabavia. Yeah,
doesn't make sense.
Why did you? I didn't fully understand your comment on that there is no stationary state for the process.
No stationary distribution for the process row. Row is not stationary. Row is not a stationary process.
If you look into the average equation for the row bar, it's again an Einstein-Uhlenbeck form, isn't it?
Yeah, but that's once you've done the limiting on the C and the P, right?
Yeah.
But if you fix the C and the P, look, I mean, the thing is, take the invariant law of the Q matrix, right? Left multiply throughout by that, you're getting the inner product of pi with rho is the inner product of pi with dl, and that's going to be a martingale whose variance increases with t.
But that's because the n to infinity limit doesn't commute with the t to infinity.
Correct. Yeah, absolutely. Yeah, absolutely.
Yeah. One has to be careful with these things. Yeah.
Thank you.
Okay.
Thank you.